Welcome to the Introduction to Correlated Materials, a series of lectures to help you understand and admire the role of electron-electron interactions in solids. Brought to you by Schrodinger's Kittens Productions. Lecture 5, the Mott transition in correlated materials. In this lecture, we'll look at two examples of strongly correlated materials that have a metal insulator transition, which is attributed to a Mott transition. We'll look at the examples of the rare earth Nicolaites and of vanadium O2. And I've chosen these examples because in both cases, it's difficult to say for sure that the main physics is coming from the Mott transition because there's other competing factors or cooperating factors which also might contribute to the metal insulator behavior, and it's difficult to say precisely which one dominates in which case. So let's start with the first example, the rare earth Nicolaites. So these are perovskite structure oxides with chemical formula rare earth nickel O3. And because the rare earth has ionic charge, has formal ionic charge +3, the nickel ion then is also +3, which means its valence electron configuration is 3d7. And in the perovskite structure, the nickel ion is octahedrally coordinated, and so the energy of its 3D manifold is split into the T2G trimer and EG dimer. And these are filled by the 7 3D electrons as shown. We see immediately that the band that forms from the EG orbitals is partially filled, and so we'd expect it to be a metal, but we also see that it's singly occupied, and so we might expect, for example, a Jahn-Teller transition to lift the degeneracy of this band and cause it to be insulating. Before we look at some data to see what it actually does, I want to remind you of one piece of chemistry, which is the Lanthanide contraction. Which refers to the reduction in the atomic or the ionic radii across the rare earth series from lanthanum on the left to lutetium on the right. And the ionic radius of lanthanum 3+, for example, is around 103 picometers, whereas when we get all the way to lutetium 3+, with its fully filled F shell, it's much smaller, around 86 picometers. So we see that the rare earth ion in the perovskite structure is getting much smaller as we go across the series from lanthanum to lutetium. Kind of hand-waving explanation of why this is when we add a nuclear charge, then as we go across from lanthanum to lutetium, then the Coulomb attraction of the outer electrons to the nucleus is increased. And of course, we're adding also an extra 4f electron, but that doesn't shield particularly the nuclear charge very well from the valence electrons. So this lanthanide contraction is going to be important for understanding the behavior across the series. So let's take a look at the phase diagram. Of the nickelates, the rare earth nickelates. So here is plotted temperature on the y-axis, and on the x-axis, the nickel-oxygen-nickel bond angle in degrees. And so here this is referring to the angle between the nickel ion in the center of one oxygen octahedron to the oxygen that's connecting it to the nickel ion in the neighboring oxygen octahedron. And if the rare earth ion, which of course is sitting here in the perovskite structure, were extremely large, then it would take up a lot of space, and these nickel-oxygen-nickel bond angles would be 180 degrees. But as they get smaller, the oxygen octahedra rotate more, and the nickel-oxygen-nickel bond angle deviates more from 180 degrees. So on this side, on the left-hand side of the phase diagram, we have small rare earths, and on the right-hand side, we have the larger rare earths. And these are labeled on the phase diagram, as shown here. Okay, so let's have a look and see what structure and properties are associated with the rare earth nickelates as temperature is varied and as this nickel-oxygen-nickel bond angle varies across the series. So on the right-hand side of the phase diagram, in the region where we have lanthanum nicolate, then the paramagnetic metal phase is stable actually at all temperatures. And then as the rare earth gets smaller, as this bond angle decreases and the nickel-oxygen-nickel bond becomes more bent, then we see that there's a phase transition which becomes gradually at higher temperature from the metallic phase to the insulating phase. At first, as the nickel-oxygen-nickel bond angle is only decreased a small amount in praseodymium and neodymium nicolate, the phase transition goes straight from the paramagnetic metal to an antiferromagnetic insulator. But as the bond angle gets even more bent, the transitions between a paramagnetic metal to a paramagnetic insulator. So the system becomes insulating even before it becomes magnetic. And it's this region of the phase diagram here where the transition goes directly from a metal to an insulator without even any magnetic ordering that's usually assigned to be the Mott transition. This region of the phase transition between the paramagnetic metal and the antiferromagnetic insulator, one could argue, is just a conventional magnetic transition that's accompanied by the transition to insulating behavior. Okay, so let's think about the trends that occur in the nickelates as we go across the series to smaller rare earths. So as the rare earth gets smaller, then the nickel-oxygen-nickel bond angle deviates more from 180 degrees, becomes more bent. And as we bend the angle between the atoms, then the interaction between the atomic orbitals gets reduced, and the bandwidth the width of the bands goes down. As a result of the bandwidth going down, the Coulomb interaction between the electrons becomes relatively more important. And so we expect a metal insulator transition with the insulating phase persisting to higher temperature as the rare earth gets smaller. So with increasing stability of the insulating phase. And this is indeed what we see in this region of the phase diagram as the rare earth gets smaller and the nickel-oxygen-nickel bond angle gets more bent, then the insulating phase persists to higher temperature before the transition into the metal phase. So the trends that we see in the phase diagram are indeed consistent with the Mott transition. But detailed studies of the structure and the magnetism show that it's not really so simple. If we go look again at the d electrons in the nickel 3+, with one Bohr magneton per nickel ion in the simple picture, we might expect to see a Jahn-Teller distortion with elongation of the octahedra. And a splitting of the EG orbitals to lift the degeneracy so that just the lowest is filled. This doesn't occur, in fact. What's seen instead is an alternation in the size of the octahedra such that one small octahedron is adjacent to one larger octahedron. And this occurs, or it's accompanied by a charge disproportionation such that the larger octahedron is formally nickel 4+, and the smaller octahedron is nickel 4+. And the occupancy of the orbitals is such that the nickel 2+ has both its EG orbitals filled, and the nickel 4+ has both of its orbitals empty. So this is a charge disproportionation transition that accompanies the metal to insulating transition. So of course one could ask oneself, is there a Mott transition, a transition in which the metal to insulating behavior is driven by the Coulomb interactions, that's followed by a lattice distortion. Or is it the other way around? Is the main physics a structural distortion that causes a change in the size of the octahedra that's then followed by a charge disproportionation, which causes the insulating behavior? And this is hard to answer. One interesting piece of information is that there's a strong isotope effect. So if one substitutes oxygen 18, which is heavier than the usual oxygen 16, into the material, this causes the temperature of the metal insulator transition to increase, which is the insulating phase with its localized electrons persists a higher temperature. And of course, since oxygen 18 is heavier than oxygen 16, it also slows down lattice vibrations, it slows down distortions of the structure, which suggests that there may be a strong contribution to the phase transition from coupling to the lattice from the change in crystal structure. So why is it so difficult to understand the Nicolaites? They're a very active area of research. To answer exactly this question of whether the phase transition is really Mott-like, if it's really driven by the Coulomb interaction, or if lattice effects are more important. And there are a number of reasons. The first is that the nickel-oxygen covalency is very high. There's a very strong bonding interaction between the nickel 3d orbitals and the oxygen 2p. And so the simple ionic picture which would lead us to predict, for example, a Young-Teller distortion is not so applicable. We can't really say it's nickel 3+ because it's so strongly covalently bonded with the oxygen. A second issue is that it's very difficult to make good quality single crystals. And in fact, they're not yet available for the whole series. And without good single crystals, then it's difficult to do a really detailed and accurate characterization of either the structure or the magnetic properties. And related to this is that it's difficult to get perfect stoichiometry in the Nicolaites. And if we have any neutral, for example, oxygen vacancies, which have a rather low formation energy, these will, of course, convert nickel 3+ to nickel 2+. The neutral oxygen vacancy leaves the electrons behind that the oxygen 2- would have. And nickel 2+, already looked at, has this electronic structure, which, of course, doesn't charge order or undergo a Young-Teller distortion. And so there are still many open questions. and a lot of really interesting research to be done on the rare earth nickelates. So let's move to the second example, which is vanadium dioxide. VO2, and vanadium, of course, has electronic structure 4s2, 3d3, and so the vanadium 4+ in vanadium O2 has a single 3d electron in its valence outer shell. The vanadiums are octahedrally coordinated, and so they also have the splitting of the d orbitals into the 3 T2G and 2 EG levels, and there's a single electron in the T2G, and so we could expect a Jahn-Teller distortion to lift the degeneracy. Jahn-Teller distortions tend to be small, for T2G electrons. And so in a simple band theory picture, we might still expect vanadium O2 to be a metal. The Jahn-Teller distortion on its own may not be large enough to open up a band gap. And so any kind of metal to insulator transition may in fact be driven by correlation. And in fact, when we look at the data, we'll see that there is an insulator to metal transition, which takes place at around 340 Kelvin, just a little bit above room temperature. And this, of course, is of interest because it means that it potentially could be used in devices since it's really a room temperature effect. So here's the original data, the first report of the metal insulator transition, not only in vanadium dioxide, but in other oxides of vanadium and titanium. Let's focus on the vanadium dioxide one now. So what's been plotted here is the conductivity as a function of reciprocal temperature. So on this side, we have high temperature, and on this side, we have low temperature. And then here are the data for vanadium dioxide. So we see we have high conductivity on the high temperature side, and then low conductivity on the low temperature side. And the transition temperature here corresponds to around 340 Kelvin. There's another aspect, though, which is that accompanying this metal to insulator transition is a structural transition. And here's a schematic of the two structures taken from this fairly recent article, which also discusses the origin of the phase transition. So on the left here is the high temperature structure. Which remember is the metallic structure. And here the structure has perfect, identical octahedra of vanadium 6 coordinated by oxygen. And all of the vanadium-vanadium bond lengths are all the same, or the vanadium-vanadium distances. In this direction are all equal. On the right is the low temperature structure, and this is the insulating phase. And here the structure is very distorted to such an extent that one sees vanadium-vanadium dimers. So this vanadium-vanadium distance is really very much shorter than this vanadium-vanadium distance. And again, this structural phase transition between this tetragonal and this monoclinic phase accompanies the insulator to metal transition. So one again has the question of whether one's seeing really a Mott transition driven by the Coulomb interactions between the electrons, or there's a structural transition as the primary driving force, and then the electrons localize in the new atomic orbitals. So can we explain this insulating behavior by just using a simple linear combination of atomic orbitals picture within really a single electron approximation, not taking into account electron-electron Coulomb interactions, but just taking into account the bond alternations? So let's just sketch a linear combination of atomic orbitals band structure, just very simplistically, and think about what happens when we have a vanadium 3D manifold, which is partially filled with only one electron, interacting with an oxygen 2p manifold, which is completely filled. We first just think about the vanadium-oxygen interactions. We'll have some very strong sigma-bonded vanadium-oxygen interactions, which will be at low energy, and also some pi-bonded vanadium-oxygen interactions, which will also be at low energy, completely filled bands. And then we'll have the corresponding vanadium-oxygen anti-bonding interactions, and these will be pi and sigma type. Then, because the vanadium-vanadium distance is not so large, we'll also have bands corresponding to vanadium-vanadium interactions. And in the undistorted structure, these bands would be half filled. The extra single electron from the vanadium would sit in this band, and so we'd have a metal. But when we make the structural distortion, then this band could split into one filled band and one empty band, with a gap. And so just in this very simple hand-waving linear combination of atomic orbitals band diagram, we see that the structural distortion which is an alternation of the vanadium-vanadium bond lengths, just like a piles distortion, can open a band gap. Although certainly Coulomb repulsions between electrons is important as well. So I hope I've given you a little bit of a feeling that actually saying for sure that a strongly correlated transition metal oxide undergoes a Mott transition is not so straightforward. And in this last picture, I try to illustrate that a little bit by showing the energy scales in transition metal oxides. Or the important and relevant and factors contributing to the energy of transition metal oxides. And what's shown, what's represented, are the Coulomb repulsion between the electrons, the crystal field splitting, the splitting into the T2G and the EG orbitals, the bandwidth, the magnetic interactions, and any strain either provided externally or as a result of these of effects such as Jahn-Teller distortions or breathing of oxygen octahedra. And all of these factors are of similar energy scales in transition metal oxides. And so they all will compete or cooperate in determining whether or not a phase transition will take place. So being able to say that really the only important competition is between Coulomb repulsion and orbital bandwidth, which would be really a classic Mott transition, is very difficult because whenever one changes the crystal field or the strain or the Hund's exchange, one also then affects these other properties as well. And so simple models, such as the Hubbard model, end up rather naive, and it's hard to really develop a very simple theory. One has to take into account all of these properties because the electronic charge and spin and orbital contribution and lattice are all important. They're all on similar energy scales. This, of course, makes the theory very difficult, but it also gives us this tremendous richness of properties that make transition metal oxides so very interesting. So this is the end of the series on strongly correlated materials, and thanks very much for listening.